if we draw a segment from the center of the sphere to the two intersections, draw segments from the center of the sphere to each of these intersection points. First place, we're going to have a picture that's symmetric with respect to the horizontal line through the center. But more importantly, we know that this is a radius because it goes from the center to a point of the sphere. This is a radius, and the radius is 1. And this distance here on both triangles is r sub I star, so that this distance here and this distance here are both square root of 1 minus ri star squared. And then for any point sample point, for our sample point, we have vertical line above the sample point it should say intersects, but passes through the sphere, intersecting at z coordinates. What's the z coordinate here? Well, we go up 1, and then we come down square root of 1 minus r sub I squared. ri star squared. And 1 plus the square root of 1 minus r sub I star squared. It follows that our region can be described, as we've seen already, by the fact that our angle theta of this line with the x-axis runs from 0 to 2 pi. So we have our spherical region characterized by 0 less than or equal to theta less than or equal to pi over 2. R going from 0 to 1, and again we've described the unit circle as it intersects the first quadrant of the xy plane, and z running from 1 minus the square root of 1 minus r squared to 1 plus the square root of 1 minus r squared. And this implies then that we have our integral, triple integral, our volume increment being r dr. Hang on a minute. It's so natural to write dr after r, but we want to do r dz and then dr d theta. And that's simply because our z depends on r. We can't integrate r before we integrate. We can't integrate with respect to r before we integrate with respect to z, for reasons that should be clear to you by this point. So there are limits on z, our limits on r, 0 and 1, our limits on theta, 0 to pi over 2. if you compare this with previous integrals we've done over this sphere, you see that these limits are somewhat simpler. Previously, we would have had a 1 minus x squared minus y squared here and here. We'd had a 0 to the square root of 1 minus x squared here. We'd have had y from 0 to 1 minus x squared. X would then go from 0 to 1. That would be with respect to x, y, and z. Here we have only one variable in our limit and no variables here. We have fixed limits here and here, which is going to make the r and theta integrals fairly easy. Now, once more, without going through the details, we're integrating our density function times our distance from the z-axis squared, and that's going to be 1 plus r sine theta times r squared, and then that's times our volume increment. Not sure I'm going to go through the entire process of integration, but probably will. Okay, we have the integral from 0 to pi over 2 and from 0 to 1 of, okay, we're going to integrate with respect to z, which is just going to give us our upper limit minus our lower limit, and that's going to give us just a 2 times the square root of 1 minus r squared. So without writing the z and indicating all the details, this is very similar to what we've seen before. We're going to end up from the z integral with just 2 times the square root of 1 minus r squared. And then that's going to be multiplied by what we have here. Now that's going to be times r squared times r is r cubed, and then times 1 plus r sine theta. And that's going to give us multiple by r cubed plus r to the 4th sine theta. And then that's going to be with respect to, actually with respect to r, and then with respect to theta. Let me fix that. Okay, it's not all that well fixed. That's not the rigid looking r I've ever written. And I didn't completely mask my mistake from before. However, okay, we're going to end up with this integral, meaning that we're going to have to integrate r cubed times the square root of 1 minus r squared, and then r to the 4th times the square root of 1 minus r squared. I'm not going to take up the time to explain all the details of the integration. However, in integrating r cubed times 1 minus r squared, we can let u equal 1 minus r squared, so that du is going to be negative 2r dr, and that'll take care of one of the r factors in the r cubed, leaving us an r squared. Now if u equals 1 minus r squared, then r squared equals what? 1 minus u. So we're going to have a 1 minus u here and a square root of u, and it comes out rather nicely in just a couple of steps. And it works out nicely that having integrated r cubed times the square root of 1 minus r squared, we can break the r to the 4th into an r to the 4th times the square root of 1 minus r squared into an r and an r cubed times the square root of 1 minus r squared, which we've already done, so we can do an integration by parts. So it really isn't that bad of an integral. But I'm going to stop at this point and say we just do this integral. We do have fixed limits, so once we get our antiderivative, it's going to be really easy to substitute our r's, and then we're going to have a variety of things. One thing we're going to have to integrate is a sine theta with respect to theta from 0 to pi over 2, but the antiderivative is negative of the cosine. That's going to be very easy.